transform the observed signal into the band energy features by using the parallel discrete wavelet transform. And by using the parallel discrete wavelet transform, we can compress input to the lower dimensional data. And we can use this band energy features to train the autoencoder. And the trained model can be deployed at the edge node because it helps to construct lightweight model. Let's look into the proposed algorithm. The proposed algorithm is inspired by the filter band characteristics of the discrete wavelet transform. However, the discrete wavelet transform has low time resolution in high frequency band. So in this algorithm, we examine the high frequency band and low frequency band in parallel to capture the characteristic of the high frequency band signal. So the first step is to perform the single level DWT. Single level DWT, and we can decompose the original input signal into both low frequency band signal and high frequency band signal. And then we can determine the decomposition level of the each frequency band by sampling the training data. And then we apply the discrete wavelet transform to both frequency bands. And in here, the scaling function is act as a low pass filter, and the wavelet function is act as a high pass filter. So as the decomposition processes, the signal in frequency band is held in bandwidth, and we can acquire the approximation coefficient and detail coefficient. Finally, we can obtain the multi-resolution band energy features by calculating the band energy feature using the coefficient obtained from the step 3. And this band energy features represent the energy contained in each band relative to the total signal energy. And given that the difficulty of acquiring anomaly data, we employ unsupervised learning method based on autoencoders. The autoencoders tries to minimize the reconstruction error of the input signal. We use the input signal as a PW band energy features, and the anomaly score is defined as the LT norm of the difference between input and the output of the autoencoder. And if the anomaly score of the input signal exceeds the threshold gamma, it could be considered as anomalous signal. To validate the proposed algorithm, we use the MIMI dataset. This dataset contains real industrial machine operating sound with background noise, and they offer a 4 kind of machine operating sound, including bell, movement, and slide wave. And to assess the efficiency of our proposed model, we employ a D-case challenge task-2 model as a comparison model. The D-case model uses the globe-bell spectrogram features, and they transform the raw signal into the 2D spectrogram image. And while our proposed algorithm transform raw data into the one-dimensional vector, and you can see that the input dimension is significantly reduces. And also, for a fair comparison, we use the same structure of the autoencoder, and the number of trainable parameters also reduced about 90%. And to compare the performance of the two models, we use use the 4 metrics. And the first metric is the AUC, which we can AUC represent the classifier's performance, and if the AUC is has a value 1, we can see the classifier as a perfect classifier. And we also introduced the unit information density, which measures how effectively an anomaly detection model compresses information. And to measure the computational complexity, we measure the data processing time and model training time. Let's see the AUC performance of each model. The orange bar is the proposed model performance. And as you can see, the proposed algorithm achieves similar performance despite they reduces the input parameters significantly and the number of trainable parameters significantly. And also, as you can see from the information density, it indicates that the proposed model includes 10 times more information than the comparison model. And also, the proposed algorithm is much more faster in data processing time and model training time compared to the deep-based model. Therefore, we can conclude that the proposed algorithm achieves similar performance with a much more compressed PDW features and construct lightweight anomaly detection model for resource-constrained action. Finally, we propose the effective algorithm for acoustic anomaly detection, and the proposed PDWP effectively extract features from the acoustic data and can help to construct a lightweight anomaly detection model. Therefore, we can say that it is an effective solution for resource constraint action.